and it's really, nostalgic to come back to this department. Although physically it looks very different today than what it was several years back. And it's also, a great opportunity to going back to basics. I have not taught DFT for a while. I never get an opportunity to teach in our department because we always get some other courses to teach. So it's a good opportunity to rewind and then get my slides back and prepare for this lecture. So today what Suraj told me is that I should talk about very basics of plane wave DFT and also connect that to ab initio molecular dynamics. So I will go extremely basics in terms of my presentation. So I am, by the way, from the Department of Chemistry, and I must say that I had a great time working with Professor Gopinathan here in this department, where I really learned the basics of, computation actually. Rest is, his lectures on computational chemistry was, I still can remember every hour because it was like a spoon feeding, and that motivated all of us to actually start doing computational chemistry later. And some of his landmark papers in the earlier years with Professor Carliuk. I don't know if how many of you are working in Hartree-Fock semi-empirical theory today. I don't know, but maybe you should see some of his earlier papers on Sindo, and it's really amazing papers actually. Okay, sorry. So I think now you are all familiar with DFT. So I will straight away head to Cornsham equations, and instead of telling what is Cornsham equation. So I apologize if you are hearing this for nth time. But I thought I will just put this slide so that somewhere I have to start, right? So in Cornsham, you know that we are going back to orbitals, although we said a lot of blah, blah, blah about density. Then finally, for practically doing things, we will go back to these orbitals. And these orbitals are, you represent these orbitals are coming from the wave in electron wave function represented in Slater determinant. And then, use that, define density and so on. Then finally get to here. I think this is already done, I guess, right? So in this expression, what is interesting is you have got several approximations in terms of the orbital representation. One is, of course, the kinetic energy, which is approximate. Then the rho of R1, rho of R2, R12 is also an approximation of electron-electron interaction. So this is also an approximate treatment, which in this formalism, you can directly translate that to orbitals in this fashion, which is very cute. Okay, and you have got all those corrections to these approximations dumped into this expression, right? And then you have got this nice exact functional form of nuclear charge electron interaction. So this is what I think you have already seen it. And what I have done is I've not written anything over density except this. I will simply keep this in this form only. Because I'm going to talk about practical implementation of these equations, so therefore I will simply keep it in this form, and then I will later tell you why I have written it this fashion. So this is okay, all of you? All right, so now the whole business starts here of how to deal with practically implementing this in the computer is that, okay, we have to somehow, this energy of functional that you've seen has to be minimized over this Cornsham orbitals. But we have to keep two constraints in our mind. One is, of course, the most important one, the orthonormality constraint. And of course, you have also the density, integral of the density giving you n number of electrons, right? So a bit of a derivation, I've skipped this part, but you can do this by yourself with this constraint. Introduce Lagrange multipliers, you will get this nice equation. Why it is nice? Because you can see this is just one electron Schrodinger equation like equations. It's like particle in a box kind of a thing with a potential V of R, right? Or V of X. So you can see this is simply a function of R1 only, X comma Y comma Z. and this is just the particle in a box like operator, right? So it looks very simple. So it's a very simple one electron Schrodinger equation that you need to solve in this form, which makes you exciting. And I must say, maybe Professor Chatterjee can correct me, I think this is the business all quantum chemists do. That somehow we boil down to a solvable equation, which is a one electron, right? So you have seen that in Hartree-Fock also. I don't know if Hartree-Fock was discussed here. Fock, right? The Fock operator operating on an orbital give you eigenvalue. So this is the same eigenvalue equation that you get. So now what I'm going to talk about is how do you implement this whole thing in a computer. Huh. Yeah. So homework exercise. Right. It's a good exercise. And figure out what is this epsilon. Right? Okay. Yeah, it's a very nice expression. So I had some connections to this to Carparnello, yeah, dynamics also, but I have skipped it. If needed, we can go back to Carparnello dynamics. There also you will see these Lagrange multipliers coming for orthonormality constraints. Okay, so how do you, I mean, I said it's now simple. So how simple is for me to go sit before a computer, program this and get the numbers out, right? This is what we're going to talk about. So, well, just I think it's again a repeat, I guess. We need a self-consistent field type calculation even if we are able to implement this in the computer. Why? Because this one electron or potential or the effective potential for that one electron Schrodinger equation unfortunately depends on the density, which in turn depends on the orbitals, and orbitals are the eigenfunctions that you're trying to solve with this h psi equal to E psi, right? So therefore you have to start with somewhere, you approximate, okay? So there are various ways of approximating. So you can have some initial guess, and then you can compute an initial density, which will give you some energy because you already got the density. And then you check with some, from the previous step of my iteration, is the energy difference less than this cutoff? Okay, this is a simple way of checking. Okay, there are one more step, advanced way of checking also to look at the derivative of E with respect to wave function or orbitals is also less than the cutoff, which is what practically all computers will do. But for our understanding purpose, let's look at the energy difference between the current step and the previous step is less than the cutoff. Okay, if not, you're going to solve that problem. Okay, with this, I mean, you're going to compute the potential. You're going to solve this problem. Yeah. Right. 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 Correct. Correct.
So this epsilon is a very small number.
Very small number. Yes.
So actually, computation will take relative.
Right.
You
Right.
take mod ei minus e I minus 1 divided by mod e.
Okay. Okay. Right.
So
Right.
that
Right.
gives you the number.
Yeah. Yeah. So it depends on the implementation. So yes, sometimes so you need to adjust to this epsilon accordingly. And also, I mean, in all practical purposes, it is simply the derivative of E with respect to psi or the coefficients, which I will come to, is what is actually practically checked. The gradient is less than a cutoff or not. Okay, so then you solve, you again get the new wave function, you compute the density, then you go back the whole loop and continue this until your criteria of convergence is met. Huh? So this is what it is, right? So this part is okay, all of you? So the only problem here is how to solve this, right? So this is where I'm coming to. So we need to somehow figure out how to solve these equations. So how many of you are familiar with H2 plus problem? In H2 plus, using linear combination of atomic orbitals, 1s A plus 1s B or 1s1 plus. So I think most of you are familiar with. So have you seen similar equation there? So 1s A plus 1s B. Because I'm saying that you must have learned in quantum chemistry 2 lecture. Most of you are chemists, right? So in quantum chemistry 2 lectures, I guess you must have seen H2 plus problem. So there you would have seen similar in school. School. But they don't show what they don't show how to solve it actually, right? Okay, so you can go back to Levine quantum chemistry and you can see how these eigenvalue equations are solved. It's a very good exercise because that's where you will understand how practically you are actually solving. And you have taken 1sa plus 1sb for H2 plus, where 1sa and 1sb can be considered as the basis functions. And this is exactly what we need to solve these equations. We need to somehow use basis. We want to invoke basis functions to represent your eigenfunctions that you are looking for, like sum over I, Ci, some basis functions, and then look for these Ci's. Basis functions are fixed, coefficients are unknown. So try to solve this problem, to find these coefficients, right? So this will yield you a matrix equation, and you can use any linear algebra approaches to solve that matrix equation to get eigenvectors and eigenvalues. And that is exactly the reason why I was asking you whether you know H2 plus problem, because that is where you first time see the eigenvalue problems in a matrix form. Chemist actually, not physicist. I think you must be seeing in physics lectures maybe in a different progression of your understanding actually. Okay, so we will use basis set as plane waves to solve our problem. The argument I'm going to put in, like why I am using plane wave basis to solve that eigenvalue equation is the following. Okay, I am interested in periodic systems. So we are talking about Avogadro number of particles sitting in my solid lattice. So, and we somehow, of course, we cannot deal with this whole stuff, right? I mean, we need to do some approximation, and the nice way we can introduce approximations to treating a solid is saying that, oh, look, there are repeating units there. So if I can solve for one of these repeating units and try to somehow take this solution to everywhere, infinitely repeated, then I don't have to solve for 10 power 23. Maybe I can only solve for 10 particles or 2 particles or 3 particles, which is part of my repeating unit, and then solve the problem of a solid lattice or the solid that I'm actually interested in. So this is where one interesting Bloch's theorem come into the picture. For any periodically arranged nuclei, the potential and the density is periodic as per this. Okay, so which means you have this translational vector L, which translates R plus L. You get back the V of R, which is showing you the periodicity. Okay, so this is how I'm defining the periodicity. That is a case, the wave function of this problem is going to be what is called quasi-periodic, where you have a periodic part and you have a phase part. And this phase part is simply coming due to the eigenfunctions of the translational operator, which is the translation of this repeating units, right? To translate this to here, 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 so infinite times in all directions. So it's coming because of that. Okay. So you've got a periodic function. So that is why I've written this part is R plus L is R. Okay, because this part is explicitly periodic, but this part is the phase part. Right. So you've got a K dot R, I K dot R here. All right. So now we have to see if I can use this theorem and use this idea to kind of treat a large solid system using the density functional theory. Can I somehow bring in the Consham equations here using this idea, right? Yeah. Both way, both it will work actually. So later I will practically show you for it is actually a repeating unit, even if it is a liquid water, which I will discuss at the end. So what we will do is it's not symmetric, but you have got, let's say, 60 water molecules in a repeating unit, and that repeats all over the place. So you're in that case, this is simply non-symmetric. It's not, doesn't have any symmetry because it's just a randomly distributed water molecules. But on translation this to all directions, you get bulk water. That's the idea. Hmm. Yeah, single molecule we are not considering now. Single molecule is an exception. I will talk a little bit later. Okay. Right now, I just trying to solve a problem of periodic lattice to make things very simple. But like Professor Herbola asked, what happens to water molecule, water set of water molecules is randomly distributed. So I'm assuming that that randomly distributed water molecule within this box is infinitely repeated to give me the picture of a bulk liquid. Okay. So right now let's don't confuse there, because we'll stay simple and then we will make life complicated at the end actually. Yeah. Onto yours, exactly. That is true. Whatever here is going to be repeated all over the place. Yeah. Okay, so because Suraj said most of you are chemists, so all the lecture notes are very simple. I was thinking the way I started understanding plane wave DFT. So apologies if it is too trivial for some of you. Okay. So we are going to define what is called a reciprocal space. So I start with the real space, and this is where my repeating system is present. Okay, so I've only showed a repeating system here. So I've made a bit more complicated. It's not a cubic cell. Okay, so you can see the lattice vectors here, A1, A2, A3. Right. So correspondingly, I have a reciprocal space which has B1, B2, and B3. Okay. And this B1, B2, B3 are defined like this. Okay. And this is cyclic. B1 is A2 cross A3, A1 dot A2 cross A3, like that. So this is how I'm going to define the reciprocal lattice. All right. So can I come down? Is it okay? So this is our translational vector. You can see N1 is some number, integer. So it could be 1, 2, 3, 4, and so on. Could be negative also, okay, because it can get translated to any directions. So it's an integer of A1, A2, and A3. So that gives you the translational vector in any direction. So I'm going to now define the volume of this real space repeating unit based on A1, A2, and A3. Okay, so for that purpose, what I have done, I've collected the A1 vector, collected the A2 vector, I have collected the A3 vector, and calculated the determinant of this 3 by 3 matrix, which gives me a scalar quantity, and that's the volume of the superset. Okay. So now these B vectors in the reciprocal space are connected to or related to this A vector, like the definition I showed you. You can, if it is convenient for you to see here, you can also use this expression, or you can also think of this expression where you can see the dot product of Bi and Aj is 2 pi delta Ij, which is orthogonal to each other in terms of Ij, but with a factor of 2 pi. Okay. So now if I look at all the B vectors, like I defined H vector by taking all the A vectors, packing all the A vectors. If I pack all the B vectors, then they are related to this H using this symbol relationship. Okay. So I can create easily these B vectors knowing A vectors, and A vectors I know because I know my real space is much more easy to deal with. So I can define my cell vectors. Okay, we just have to do the inverse of the transpose and multiply by 2 pi. So I get the columns of B vectors, which will be these vectors in the reciprocal space. So this is just my definition. So because I'm going to go to the next step of defining plane waves and where all these ingredients will get there. Okay. So if you want, we can also come back after seeing the next slide. So this is how a plane wave will look like. So you can see 1 by the volume of our supercell. Okay. And EIG dot R. So what is G? Right. So G is 2 pi H transpose inverse, okay, which is your B vector multiplied by 1 or 2 or 3 or 4 or 5. So that's your G. This is simply a triple of integer values. Okay, that defines your reciprocal vectors. So you're just going to define G in this fashion so that you have seen now the connection between your A vectors, because that's easy to see. Okay, so you can see the direct relationship of your A vectors to the reciprocal vectors that I'm going to define as G now in this fashion. Okay, so this is the G which appears in the equation of plane wave. So the plane wave at some value of R is basically this quantity, okay, for any given G. So now what we have to do is somehow make use of this function to expand the wave function. So the way I'm going to expand is that, so I say, okay, I have some periodic function. So I'm going to simply expand it over all the G vectors. Okay, so I have some coefficients of expansion, and these coefficients of expansion I've simply used as psi itself. I should not have used psi, but just to make life simple, I've just used psi of G e power I G dot R. Okay, so this is simply like C of G, okay, e power I G dot R. This is exactly like you have seen Gaussian basis, sum over Ci Gi, okay. Same way, you have instead of Ci, so I've got something that depends on G, that's your index G, okay. In your plane wave basis, you would have used it as I, small I guess, if you have seen that already. So now why I wrote it in this fashion is because I would like you to see a nice relationship, because you have seen Fourier transform in your basics lectures of mathematics and so on. So you can go from a time dependent function to a frequency dependence of that function by doing this forward transform e power minus I omega t. Okay, so t is converted, the function is dependent on t, which is now a function of frequency. So you can see I can also go back from frequency to time by doing inverse Fourier transform. This is where you can see plus, I mean it's too small, I omega t. And if you look here, you see that it is something like this, right? So I'm going to see some kind of relationship when I expand this over plane waves. I see they are related by Fourier transform. So I'm going to make use of this relationship all throughout my lecture, because right. Correct. Correct. Exactly. Correct. In the momentum space, yes. So actually, it's very difficult for a chemist to go to that level because solid state physics they have not learned. Yeah.
Frequency time we learn
Later, yeah. All right. So, is this okay? All right. So, one interesting property, the other property that I'm going to make use of from the plane wave basis is the orthonormality property. I guess this also, I don't know if you have seen this before, but I'm just going to repeat it. So you have a plane wave, okay, and you have another plane wave with a different index. One is g and other is g prime, and naturally they are orthogonal to each other, okay. So this is very interesting. So because this will simplify a lot of integrals that will actually you have to calculate while creating the equations for solving Cornsham equations. Yeah? I'm going to come back to this expression, but just keep this with you. Yeah, sorry, that's a typo. Yeah, that's a plus. This is minus because this is the complex conjugate of this. Yeah.
They can do it by simply like just expand it to write it as say hospital precise and
Right.
Then you see very easily how to integrate.
Right. Okay, so now there is another important relationship that I'm going to make use of going to the plane waves is this style of integrals that you need to deal with while solving the Cornsham equations is you see this is over the R space, the real space, okay. I've got some integral, let's say psi star of R, psi of R to calculate, okay, which is the overlap, right? So I integrate this over this entire volume where I have to calculate this integral. I convert A to G space again using the plane waves, right? So then I get something like this. This is okay because A can be expanded over G and B can be also expanded over G, but don't use the same index because that's an independent expansion. So you have to use an index of G prime just to distinguish the two sum. So if you do this, you see that this is already omega times delta G prime, which I just showed you, which means an integral of this fashion will simply a sum of the G components, the the reciprocal components of A star and B. It's very easy to calculate. You have to just sum over G and what are these values in the G space, and you will get this integral. This is exactly identical to that you would have calculated in the real space. So if there are integrals that are difficult to calculate in real space, I will go to G space and compute this and get the stuff, okay. So this also going to simplify a lot of things in my practical implementation of Cornsham equations using the plane wave basis. So these are the two important things that motivates me to seriously look into plane waves in in solving the Cornsham equations. So now we will get back to this and do a proper expansion of Cornsham orbitals in plane wave basis. So I gave you only a bird's eye view earlier, but now let's get into the details. So this we have seen, and this also we have seen, right? We have seen that the Cornsham orbitals will have this block form if we go for a block form, right? And this part is periodic. And I said, okay, if it is periodic, let me now expand that periodic part using plane wave basis, because plane wave basis is naturally periodic, right? Now, yeah. So no. It is coming from here. So you have calculating this integral for a given G and G prime. It's a direct delta function only, okay. Sorry, it's actually for any if G is not equal to G prime, right? It is not continuous actually. No, it is not. So you have got G and G prime. For any G equal to G prime, it's 1. Okay, G is not equal to G prime, it's 0. So I just thought that you all know about it. So it is delta Ij, I equal to J is 1, otherwise 0. Okay, so it's just I and J, that's it. Okay, right. No, it's not Dirac delta function. It's a chronicle delta, like you have seen also this earlier. It's exactly this, no? So where exactly is your confusion? Which integrals? Okay. No, so but delta Ij has nothing to do with integrals. It's just asking whether I is equal to J or not. Yeah, it's just a notation of simplifying actually the whole. Yeah, go back. I'm sorry. How is this omega coming? Okay, so that is just a normalization of this, because if you just have this as 1 and integrate over the entire space, that's a volume. Okay, so, right, so now in this case we have the periodic part is only this uj, right? So I can expand uj in terms of plane waves because that's a periodic part. I mentioned that earlier. So I'm going to use a plane wave representation. Now the equations are going to look a little bit more complicated. These are the coefficients of expansion of this periodic function using this. I'm sorry. I think I have. Did I made a mistake? Okay, sorry. I think let's look at here this part. So I think I made a mistake somewhere. It's fine. Right. Correct. No, I think I should not have this equation is not correct actually. Yeah, I think you can look here. Yeah, you can go back here. So you have this eik dot r coming here and sum over g cj. Yeah, I think this should have this. It's a small mistake actually. Yeah. So this is the expansion. Okay. Then you had already e power I k dot r. Okay. Due to the Bloch's equation. So this is your u, which is periodic, and this is what you are going to expand over the basis function. This is part okay? Which you get. Yeah, ig dot r actually. Yeah, correct. This is when you start typing at late night. This happens. So finally, you can see that coming from here, taking this inside, you get Cg e power I g k plus g dot r, and that's going to give you this. So this is your Cornsham orbitals in plane wave basis. Okay. Any doubts? All right. So now let us simplify the whole thing. Let's consider again in terms of a chemist point of view. Let's think of solving this problem for a given value of k. Okay, because you have to also now think about how to get the whole k. Okay, right, because of the wave vector that is present in our Bloch's expression here. Okay, so you can solve for a given k this eigenvalue, right? Equation. I mean, somehow we don't know how. We will see how we will solve it. But I'm just going to tell you that we are going to solve for each value of k. Okay. So just to give you a simple introduction to these k points. So see, so what we are interested in is actually the primitive cell which is there in the reciprocal space, which we will call as Brillouin zone. And the first Brillouin zone will cater to most of our purposes, right? So there are several interesting points in this first Brillouin zone which we will include in our calculations. We cannot have all the k points that are possible to include in our computation, because there will be like infinite number of independent Schrodinger equations that to be solved. So what we will do is we will simply stay with first Brillouin zone and discretely do any integrals over k points. Okay, we have to solve for each k point one Schrodinger equation, right, or Kohn-Sham equation. So now there are a lot of interesting points in Brillouin zone. So we have to have some clever ways of identifying which k points to be chosen for your calculations. And if you know it, integrals, and you sum over all these k points, ideally these integrals are like this. Okay, you have a continuous integral over k and some function of k, which will now be used like this, because we will only be doing over discrete points over k, and that will be sufficient if your the lattice point, your real space supercell itself is sufficiently large enough, then you, even if you miss some k points, you don't have to worry about it. So for example, for most of the condensed matter systems, like Professor Arbolo asked what happens in case of liquid water or so, then we generally use a large real space vector. Then you have seen the reciprocal lattice will then keep shrinking because of that inverse relationship. So you don't have to have so many k points, or possibly no k points other than k equal to 0, which is called the gamma point, to be included in your computation to get reasonably good predictions. Okay, so this is the trick we will use. Either you increase the real space, then we will only stick to k equal to 0, which means large supercell, or if you are using a small supercell, be careful on choosing how many k points, because your total energy calculation will include an integral something like this. Okay, so there are various ways in which you can do. One is this Monkhorst pack approach, which is, I think, possibly there in almost all the code, and so which provides you how to choose the k points, and you can use those k points if you don't know how to exactly do it. And other way to check it is to increase the k points and see whether you are getting the energy converged properly or not. So this is critical, but be careful. Don't be very picky here because computational time is going to increase significantly, because you have to solve for each of these k points a Schrodinger equation. So then the computational time will explode. So you have to make a good choice. Either increase the real space, supercell, and then only worry about a few k points or relevant k points. Yeah, you had a question. Hmm. Oh, okay. So that's because of that inverse relationship. In fact, I don't have those equations here. The volume of your reciprocal lattice is inversely proportional to the free this thing real space, rare space, right? So if that is very large, the other one is small, then the main point is your gamma point, which is sitting as a center, right? The k equal to 0. So that's more than sufficient, because that accommodates all your weakness size cell in the reciprocal lattice will shrink and shrink and shrink. So that naturally tells you only few k points have to be chosen. The first brilliant zone, yeah. Yes. Then only for k equal to 0, you do the entire Schrodinger equation. Just one calculation, one set of calculations. Oh, I mean, there are many integrals over g left or r left. Yeah, k points now. So for this is a practice that people use if the real space, I mean, supercell is not having any symmetry, right? And you like bulk water, for example. So water molecules are randomly distributed. So you take large, sufficiently large enough in real space, and that makes sure that the energy is converging, right? So that's what usually people do. Okay. Yeah. 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 Localized. Yeah. Yeah. Correct. Correct. So for it, it's a metallic system or something, then you have to. But there also, if it is a liquid ammonia, for example, there's no way we can do k point based. Because it's all correct. Exactly. Yeah. But it's still delocalized. But how do you calculate? I mean, the k points there. You need possibly very large k points if you take a small supercell there. Yeah. Correct. 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 Yeah. Right. 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 Yeah. Yeah. Will not be sufficient. Yeah. Correct. Correct. Sorry. Correct. 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 Yeah. Yes. So why is it one? Because you have one side is vacuum. Okay. So your energy is converged. Okay. Yeah. No, no. So yeah, you have to do the convergence of if you 8 by 1 is converged, that's good enough for you. Ah. No, 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 no. That's less. Yeah. Yes. Correct. 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 No, 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 no. So you don't have to do for supercell, unless this you have a symmetry in this lattice, right? So you just have to increase the k points. That's it. There is no need to change the real space. The number of k points, right? Hmm. I think particular cases we can discuss maybe later. Okay. So yeah, this is the standard practice. Yeah. Yeah, so that's why you have to balance the. See, if you have in those kinds of system, you have a choice of increasing k points without worrying about the real space part, right? But there are systems where you cannot do much because the system is already, yeah. I mean, random. Okay, so you don't know whether that initial supercell that you've chosen is going to represent your entire periodic system, right? So like liquid. So that's where another problem comes, right? So that's where I'm saying that you will have to think about increasing the real space supercell also. But for a period is like solid, I would not. Yeah, yeah, is more than enough. Yeah, it is localized, but exactly, exactly, correct. Okay, so now I will slowly go forward. So that was just the basic stuff on which we will now build up the whole quantum equations using plane waves. So let me just do a very quick derivation of the kinetic energy of a plane wave. So this is like particle in a box type kinetic energy operating on e power g dot r. Okay, you can see that you easily get very nicely get this expression g square by 2. Okay, so I'll give you the slides after doing any corrections that are needed.
Square by 2
Yeah.
and you p square by 2.
P square by 2m. Then you will see the momentum also. Exactly. The same thing. Same. Exactly, exactly. Correct. So now, yeah. Yeah, yeah. Sorry, sorry.
See, it is better if you put
Yeah, sorry, sorry. It is plus actually. Yeah. Right. I will do this correction. Thanks. Okay, so now we use this fact that V of G converges rapidly with the modulus of G. Okay, that's the, if that is the case, then for each k point, we will only consider G vector which is less than a specific cutoff, because your V of G is your potential or Vs of G, which is entering your quantum equation. So if it is converging with the modulus of G rapidly, then why do you choose large number of G vectors in your computation? So you stop taking G after a while, and the way we can do that is to use the kinetic energy that we derived earlier, use a constraint on the kinetic energy of the plane wave. Say that if the kinetic energy of plane wave is less than the cutoff, then I consider. If it is more than that, I am not going to consider. Instead of saying, okay, this G vector I will take, that G vector I will take, so I don't have to worry about it. A single parameter like this parameter E cut decides what is the value of G that I should consider in my calculation. Okay. So since we have to solve that for each k point, so I'm going to bring in the kinetic energy including k. So this is actually our parameter that decides how many G vectors should enter in my calculation. So you have sum over G, you remember, right? Expanded over the plane waves. So that sum over G is going to stop at some point, and that point is decided by this single parameter E cut. Okay, so this is simply decided by the kinetic energy of the the plane waves, which I just derived in the previous. You can actually show that the number of plane waves that enter into our calculation, because it's kind of a circle, it's like a circle, right? Equation of a circle. So I'm going to represent all these G vectors in this mesh of G vectors. So what I'm showing that only these G vectors will enter my calculation. The rest of the guys are not come. Okay, so if you think of some wave like this, okay, that wave will enter into my calculation only if its G component is within this circle. Okay. So possibly this will not enter my calculation because it's high frequency. The G value is going to be very high. You can see that, right? So it may be somewhere here. So I'm not considering that G vector into my calculation. So I'll only consider those which falls within this circle. Is okay? And that number of plane waves that enter into your calculation can actually be calculated from this E cut that you choose and the volume. And you can, for any of the calculations that you are doing, you just take this equation and compute by yourself, see how many plane waves are or how many G vectors are going to enter into your computations. Okay, because this is going to decide how big is your matrix, the Consha matrix, and the computational time and so on, right? So it's good to see how big is this. This is 10 or 100 or 1000 or a million. Okay, you can check that. So I'm sure you would have done some exercise by changing the cutoff E cut, and you're going to see, how energy is converging with respect to cutoff, which decides, like uh, what to choose, what cutoff to choose, and so on. And uh, I mean, it's very important that when you are comparing energy of one system and another system, just try to be consistent across, because I mean, we are always making an approximation. So make sure that the approximations are done equally on the two systems A and B. For example, you're calculating adsorption energy of a molecule on a lattice, right? So just make sure that your cutoff is kind of is the same, or make sure that you have reached sufficient convergence in the total energy. Okay, so now we fixed one problem of setting an upper limit to this sum, right? And we also saw there are advantages that's going to come to this, any integrals that we are going to evaluate with this expression, because of the orthonormality, and also the fact that we can simplify integrals using this simple approach, right? So now I'm going to plug in this to various various things and see how easy or nasty it's going to look like. Okay. Yeah. Yeah. It's a sphere actually. It's a sphere. Yeah, absolutely. Yeah, I mean, this is also not a wave in 1D. It's also in 3D, and yeah. So. Yeah. It's clear, right? I mean, I cannot draw the. I mean, I can draw, but I didn't. Correct. Yeah. I mean, R is a vector. Yeah, sure. Yeah. Correct. Exactly. Yeah. Okay. All right. So we had a very simple expression in real space with the Cornsham orbitals. It's just the square of the Cornsham orbitals gave you the density, the mode square. Okay. So let's see how that is going to look like in Fourier space. Right. So I have not written one step. Okay, so we have the expansion of your psi in terms of g, right? And you have another psi star also in terms of g. So you need to use two different indices, g and g prime. You can see the two coefficients that are entering here. And of course, we are talking about density in real space. So you have to integrate out the k points. So you're going to have this integral over k coming in. I missed again dk here. I will correct it actually. So you have sum over g, you have a sum over g prime, you have an integral over dk, and you have to calculate this integral to compute the density in real space R. Okay, is this equation okay? So F is an occupation, so you don't have to worry about it right now. You can skip this part. Let's assume that we will only assume that every orbital that we consider is singly occupied. So we don't have to, for simplicity, let's forget about this. So now to make this into a simpler form, so I'm going to do a small trick. So what I'm going to do is I'm going to substitute Q as G minus G prime. This is also some G double prime if you want. Okay. So you can sum over Q. Okay. Sorry? How is? Yes, there is a sum over. This is an integral over k actually. That's why I missed that dk. Yeah. I will correct that. So this is an integral over the k vectors. Okay. So I've not put that sum over k because there will be too many sums. Just avoiding that, I did this, but I forgot to put dk. So there's a dk. Okay. So this part can be translated into this form. Again, you can try by yourself, just by substituting g prime as, you can g minus q, okay, and g as g, and this will become e q dot r, right? So this is then can be written something like this. This is rho of q, because this entire part is going to depend on q, this entire thing in the round bracket, okay, and e power I q dot r. Okay. So I mean, you're not going to do any simplification here, but you can see something interesting. So this is the density in the q space. Okay, q is also sum over g, because that is g minus g prime, right? So I have already brought it in here. It's independent of. So these two things will be fall. I mean, should have been written within this round bracket. By the way, actually, yeah. So what is important is, therefore you have density in Q space. Doing a Fourier transform to density in the real space. Now, why I showed this equation is one important factor, is that because this Q now will be over all G's and G prime with G minus G prime, the number of G vectors that you have to take is much larger than the G vectors that you should have taken for plane wave expansion, because of this G minus G prime.
To get the rho of q,
Yeah.
you are doing 4 operations simultaneously. Summing over j,
Yeah.
integrating over
K,
again summing over
G, and
multiplying by l.
correct, exactly. Yeah.
And then multiplying, of course, series the S1.
Correct, exactly. That's true. Yeah. The tricky part is how much is this Q? Because of the G minus G prime.
Is a vector.
Q is a G, actually it's a G double prime.
So you are doing summation of several vectors.
Correct. So therefore, this radius, which will pick the G vectors for this sum, okay, is going to be bigger than the E cut that you have taken. That is the message I wanted to give you. So, yeah.
Since we already said
Yeah.
that beyond cutoff P is very small.
Yeah.
How important is it to have row components beyond that?
For the G, we need actually. The problem is that as we multiply functions, they get compact and compact. So this problem will also come in some implementation of this exchange correlation also, where the functions are becoming compact and compact. You need.
So I cannot entirely assume that row.
So here it is clear. Here it is clear, because here it's clearly 4 times the cutoff, because the maximum you have is 2G, right? Maximum you go 2G, and so therefore there I know the square of 2 is 4.
Actually, you could do a very simple exercise.
Yeah.
Let's say Fourier transform.
Yeah.
Write, let's say, coordinate space representation of the wave function psi from R.
Yeah.
And then suppose you plot this psi of R. You see a picture.
Yes.
You go to the momentum space.
Correct.
Plot, let's say, phi of P.
Correct.
You see if this is distributed, that is getting
Correct.
You can always see.
Right.
Only then you will get the Parseval's formula that normalized in both sides. Like integral psi mod square
Right.
dr
Right.
would be same as integral phi p mod square d. That means in the two spaces, they would be normalized.
Correct. That is true. Actually, this this is just a practical aspect. I mean, it's not to do with any. Yeah. Okay. Yeah. Right. Acha. Okay. Sure. Absolutely. Yeah. So that factor will come, but this particular case is just coming. You can directly see that why you need 4 cut. Yeah. And possibly you don't enter this in your input file because it's automatically taken by the program. So you don't really realize that you need a bigger cutoff for density. Yeah. Yeah. Yeah.
Is K a continuous variable? As far as I see, we bring it via UK.
Correct. Correct.
There, K is quantized in the sense that the plane wave V, I, K are the
Correct.
log function K is supposed to be
Correct.
quantized.
Correct. Correct. In a periodic system, yeah, K has to be continuous, right? I mean, like I mentioned here, right? Think of a free electron floating in the lattice. Okay, it's a continuous K, or you can have all possible momentum, right?
K is just moment. K is closest to
Free particle,
momentum of the particle.
but we can't do that practically. So, right? So we'll try to have either selected K values which contributes most to the sum, or we will only consider K equal to 0 because our real space is large enough. The Wigner cell which is there in the reciprocal space is very small.
But at the stage of numerical calculation, obviously that is.
Yeah. That is what I said. I mean, this is what I'm assuming. I only problem is that I didn't want to write sum over K again because there are too many sums, and I mean it is also possible that f of K can be a function of K as well. Okay, so but it doesn't matter right now. I'm just going the message of this slide is about the cutoff, which is different for expanding density on the Fourier space. Q is another G. Q is another G, but that G has a different breadth actually. Okay, so it's from minus 2G to plus 2G. Maximum, yeah. That is what I'm saying. So because you look here, Q can be 2G, G can be negative, right? So it can be 2G. So if it is 2G, then it should be 4 times the kinetic energy cutoff. Okay? Yeah.
In K space,
Huh.
kinetic energy is not a differentiable. It's a multiplication.
Right.
Whether it is necessary to do differentiation and solving a differential equation.
Okay.
In K space, remember, kinetic energy is just K square.
Correct.
Square by two.
Correct.
You don't have to bring any Laplacian.
Yeah, I mean, if it is kinetic energy only, then it's simple. I mean, life is simple. Free particles. Okay. So finally, whenever I have to break, you just let me know. Okay, 10:30. Okay. So I have this as my kinetic energy of the entire system that I'm talking about. Okay. So half G square. Okay. But you see, because I have now psi expanded over coefficients, I'm going to have this c square as well. Okay. And you have, I mean, this is occupation number, you can ignore it for now actually. I will remove all this, make it a bit more neater when I give you the slides. And I have integral over K, sum over K. I is running over all the number of electrons, or all the number of orbitals that you are considering in your calculation. And G, as I told you, it runs over the cutoff that is defined. Okay, so in the Cornsham equation that we have to solve, that's where we started. We have got one ingredient ready in computing in the plane wave basis, which is this and this. Anybody, all of you can implement this. If you have to do that in 2D, you just need a 2D mesh of G, okay, and sum over orbitals sum over k points, take k is equal to 0 for to start with. You see, it's just 2-line code to do this, right? So simple to calculate the kinetic energy of your system with plane wave. Okay. But the difficult part, like Professor Chatra said, kinetic energy is a simple thing. rest.
Ask Fourier transform.
Yeah.
Actually, this, you want to solve
Yeah.
differential equation. Numerically for different function.
Yes. Correct. Yeah.
So it is like this. Say you.
I think they
jump between two different.
correct. I will come to that.
You do the kinetic energy part in the momentum space.
Right.
So it is multiplicative. But there your potential energy is integral. And in the coordinate representation,
Yeah.
kinetic
So I will come to that part actually. Yeah.
potential energy is multiplicative. So you exploit both the spaces. Go to the momentum space, calculate the kinetic energy part.
Right.
Come back to the reciprocal space, and there you do the momentum, this potential part which is multiplicative, and go back and forth. So
Yeah.
you can solve.
I will show you. I'm going to show Professor Chaturaj on this. So so this kinetic energy part is okay, all of you. So now we have another beast, which is the potential in the Cornsham equation, right? You remember the Cornsham equations, right? You have like particle in a box like stuff, and then you have got a potential which is also kind of one electron potential. So this V is only a function of x comma y comma z. It's in Cartesian space. Okay, like Professor Chaturaj mentioned, although it has several parts, I have explicitly not included some contributions here, which I will add later, not to confuse you. But we have got this external potential again as a function of x comma y comma z, which is coming from the nucleus interacting with the charge density rho of r. Okay, it's a very simple term.
Actually, I think technically
Yeah.
it is better. Also in some
Yeah.
cases you will see
Yeah.
the potential should not be written as a function.
Functionally, that's why. Yeah. Correct.
Energy is a function.
Okay.
When you take its functional derivative, you may lose the functional nature.
Correct.
Isn't it?
That's right. Yeah. So regarding then this is the Hartree part, which is the rho r1, rho r2, integral dr1 dr2. That part is contributing to this potential. We don't know how it is, and the the exchange correlation. Right now, I have simply written as a function of rho of r. Now, how I'm going to no, I have explicitly written. I will go to each of these guys and iron it out and see how I can practically implement in a computer, right? I mean, that's what I thought I would do, because then you know what is happening in the code which is running behind you. Okay, so I have now clubbed many things in this equation. So I will go one by one. Sorry to make the life difficult, but there is one cute thing here, and I wanted to, I want you to take it with you so that you appreciate. Although this electrostatic part, now I have introduced electrostatic part, which includes all the electrostatic type terms in your Cornsham equation. Okay, one is the Hartree part, rho r1, rho r2, r1 minus r2. Okay, in fact, practically this is very simple to calculate in real space, right? You have just a grid on which the density is. You already know the density in each of these grid points. You can very easily compute it. Okay, and you have got the charge, the nuclear charge density interaction, and that part due to the core, with the nuclear core, I have written as a potential itself. Why I have written as a potential, I will come to you in 1 minute. Okay, so this is integral over dr and sum over I, because each nucleus has a potential to contribute to this. Is okay? So there are two nucleus. The nuclear charge of these guys are electrostatically interacting with the density, which is density into the charge of electron is another charge. So you need to take care of that.
All nuclear effects you are trying to put it as
See.
it is coming from the electrons.
No, I will show you.
Using electron is very
No. It's yeah, exactly. That's what I'm going to do. I will show you how I'm going to do this. So that's why I thought this is a very interesting slide. So now I'm also introducing the nucleus interaction. See if you're, because that's also a contribution which I did not bring in earlier in the Cornsham equation, but I'm just introducing it here because later I'm going to go to ab initio molecular dynamics where that part also become important. This is simply the charge of the nucleus, charge of the other nucleus interacting using a Coulombic form. Okay, so now let me tell you a trick, okay, which most of the plane wave codes are doing, is that the nucleus which is sitting here at Ri in the grid space, right? I mean, we have a grid where the electron density is, but nucleus is sitting here and here, right? So I will put a Gaussian function with some width. So the charge due to this core of the nucleus is approximated by a Gaussian function. Okay. So then this part, this potential is simply this will be an error function because it's an integral over the Gaussian. Okay. So now this is quite a simple expression to do, and I can make use of this, of the features of this equation, which I will show you very soon. Okay. Now I'm going to define something called dot. Yeah, sure.
Why putting a minus sign in the row? Because this is a nuclear charge.
Is it in
You're
the
going the other way.
Is it in the yeah.
What is the difference between R and R prime?
So it is just so in the grid you have two grid points, independent grid points, right? So you are calculating the potential at a point R. To calculate it, you have to integrate over all the other grid points R prime.
If it appears that R is also one of the set of electronic coordinates.
No. Here actually no. There is no electronic coordinate in this case. Here because it's a density. So density is sitting on a mesh. It's just a mesh point.
Yeah, but in that case, you
Yeah.
put a capital R.
No. Capital R is actually we have reserved for the nucleus. So because I am here, I am not bringing in electronic coordinates at all anywhere. I mean, so okay, we'll see. Just consider R as just consider R as all my talk. Just one grid point here. Just that, because that's because in the density functional theory, correct, space, yeah, correct, exactly.
The whole idea of where you are doing the integration in true sense,
But
bringing in to the discretized form.
no, but we don't need it in Cornsham DFT, no? We can discuss it actually. Huh? So, yeah. Oh, yeah.
Just clarify.
Yeah. I think next slide will clarify many things. Yeah, sure. Yeah.
How much error does it make if you make a Gaussian?
Yeah. So usually there is a. I mean, this is coming from a database that we have to write. We have to have this parameter RIC. So it will have error, but will it affect anything is a question. I mean, I don't think it is, because usually it is taken as the you take the how the density is or the wave function is decaying, or the you look at the atomic. Oh, sorry. No. I will. That's what I'm going to see that actually. So you can see there is a a point after which your electron density is having a deformation. So you take that as your the core density. You take that as your cutoff actually. So that's where you have. So it's something like you can say covalent radius, right? I mean that is something.
RIC would be, say, calculated within the program?
No, predefined, predefined, yeah, predefined. Usually this comes from pseudo potential, because pseudo potential already has. I have not introduced to them pseudo potential, so yeah, yeah. It is. We take it from the pseudo potential. Yeah.
You are doing it by hand at the beginning itself.
Yeah, exactly. It's not a computed ab initio. Yeah. Now, why I am doing this trick is what I was excited to tell you. Huh. Is it okay if I show this slide and take your question? Because I think many questions. All right. So now I am creating a charge density of the core just by adding all these Gaussians centered on all these nucleus. Okay. So I have again a density on my grid point due to the nucleus. I have density due to electrons. Right. So two density. So total density is these two guys due to the nucleus and due to the electron. So now rho, now if you have to actually calculate the electrostatic energy, I don't know if this derivation was already done. If not, I will give you this derivation. Rho of R this integral in Fourier space is this cute little equation. Half factor. Yes, exactly. So Prof. Chadraj knows every single details. So look how cute it is. It is the total density in G space. I can Fourier transform to get to G space. This is easy to get. This is easy to get. I cannot sum over calculated at G equal to 0 for all other G points. This is simply this, and this non-italic, I mean this italics G is the absolute value of the G vector. So in one single shot, you got all these B's done. Okay, and that's one advantage. Of course, you need to have a few more terms will come because of the periodic nature of the electrostatic interactions that are present within the supercell to the next cell and so on. So you have got a sum over lattice, and this equation, if you are familiar with Ewald summation, this is nothing other than that actually. Yeah. So it takes care of your entire electrostatic part. Yeah. Of condensed matter systems. Yeah, sure. I think she had a question. Nuclear charge, yeah. Oh, okay. That is just substituting that actually. So you have an integral over R of this stuff. So integral of Gaussian, it's that contributes to the error function. You can try it out. Homework exercise for you. Yeah. That I will come actually. Technically no, right now, but I will add that explicitly. Yeah. Yes. That is my next part of the lecture actually.
At least I'm getting confused again.
Yeah.
Core has nothing to do with core electrons. Actually,
Yeah.
nucleus is playing the role in such a way
Yeah.
that it is as if you are bringing the nucleus to the status of the electron and creating a common type of potential.
So there is no electronic coordinate here actually. That's what I wanted to, because it's just the matter of how to compute integral dr prime rho of r prime.
No.
Actually,
yeah. It's a shift of gear.
I know. Actually, his question was is a very relevant question, because the nuclear charge how are you going to really consider whether the core and valence? That's yes, I will come to, because I have not introduced pseudo potential. When you introduce pseudo potential, that naturally will get in there. Correct. It is a screen. I mean, it depends on how you are going to treat it. So I will come to that in the very soon. Actually. No, no. That is pseudo potential is more complicated. Yeah, yeah. Yeah, yeah, right. Correct, correct. It's a frozen core. Frozen core. Can you continue? Yeah. Yeah. All right. So I've not given, as I told you, that all the derivation here is not given because it's identical to eval summation. So you can read about eval summation, and because it's a pretty long derivation, so I have not shown. This derivation is just a one-page derivation. I will add that slide and provide in the slide. Yeah. So this, please look at any books of molecular modeling where eval summation is mentioned. You will get these expressions straight away. Okay. So now, how the code is doing, right? So code actually starts with the coefficients, generating coefficients in the G space, your any plane wave code. Okay, and remember, this is a complex number. This is a complex number. So you can get the psi in R space, which you can then visualize on a 3D grid using cube files and so on, using an inverse FFT. But inside the heart of the code, this is the fellow who will be taking care of most of the operations, right? Of course, if you want to look at density, you also want density in real space. And not only for visualization purpose, many other parts of the Kohn-Sham equation that you solve is actually in real space, which I will show you, for which you need density in the real space. So you calculate this, but then you also compute this in real space. That is simple, because sum over I psi square will give you this for all the grid points. Now, once you have density, you can compute many potentials. For example, exchange correlation potentials are often computed in the real space. So you can calculate that with some expression, which I think you will see that when exchange correlations are dealt with. Okay, so that will give you this potential. Then, if you can also calculate rho of G, the equation I showed you, what will be that? That's a forward Fourier transform. Okay. So this was already an inverse Fourier transform. Now we are going forward Fourier transform to get rho of G. Once you have rho of G, I just showed you how to calculate the Hartree potential and the entire electrostatic potential. Okay. And you have the choice of keeping this in real space or in G space. But what we will do, we will actually convert into real space, for the reason that this fellow is in real space and we don't want to convert right now that into G space due to some specific practical problems. Okay, I think most of the codes are doing like this only. So you get the Hartree potential in real space, sum it up to get the Cornsham potential in real space. So, but actually for solving Cornsham equation, you need H psi or F psi, which has V psi, right? We already have psi in R space. We can multiply. So that multiplied quantity which is there in real space, you can do an inverse Fourier transform to get the potential in G space. I mean V psi in G space. Now why you need V psi in G space? Because you have to finally diagonalize this beast. I mean number of G vectors, just check your calculations how big it is. It's a huge matrix that you have to diagonalize, and I'm going to make use of some property of representing this Cornsham, this V psi matrix in G space to diagonalize it in some specific manner. Okay, so therefore I need this in G space at this stage. Okay, V psi, yeah, V psi into yes, V psi. Remember, V psi is also the gradient of Cornsham equation with respect to psi. I mean, of course, kinetic energy has to be added, but that's a trivial thing to add, right? Because kinetic energy plus potential energy, psi is your del Cornsham energy with respect to orbitals, which you have seen somewhere. This one. I'm talking about this. I need to solve this. I say this is what I am calculating. Kinetic energy plus the potential energy. This is now in real space. I will add the kinetic energy, okay, and psi, that will give me this entire matrix in real space. Oh, sorry, in G space. That's what I'm doing here. So this whole thing is in G space. Now,
So your Laplacian operator is not there.
yes. Correct. That's a beauty. So this is where we have to actually, our practical businesses start here, right? I mean, this is where the computer really has to do its work for solving this equation, and this is the hard part. And you, I don't know how many of you are familiar with these kinds of matrix form of eigenvalue equations. If not very comfortable with, please look at this most simplest thing that you can think about is H2 plus problem. Okay, and how to get these eigenvectors. Each column is an eigenvector and the diagonal elements are eigenvalues of these. Yeah, orthonormal, yes. Yeah, this equation is already built with orthonormal. No yes, yeah. So immediately your Levine will say, oh, this is easy to diagonalize. Yes, you can diagonalize, but think about the size of this matrix. It's just on the G space is huge, not possible to do direct diagonalization. It's too expensive. Remember all these diagonalization procedures, whatever you are familiar with, all of those scales n cube. If n is 10 power 6, okay, 10 power 6 into 10 power 6 into 10 power 6, that's quite a big number actually. Okay, so we can't do this. So what practically people do? So people give you two or tools to do this. One is the most simplest approach, which is called direct minimization. So how does direct minimization work? Okay, I missed something. One small equation I missed. So your total Cornsham energy, right? It's a functional of R. So you can do functional derivative with respect to R, right? So from this you can calculate how del Ci is, how the coefficients of expansion of wave function will be with respect to C, right? So you get a gradient of how to move either your, to make it simple, you can actually think of this, right? you can think of, right, this one. So your Cornsham orbitals, how you are going to change with respect to E, which is what I derived already. That is nothing other than H psi, H into psi. Okay, that H psi is now in G space. Okay, so what you can do is that since H psi is this, H psi is this, no? Not getting? Okay, so take so what is H psi? You have to take derivative with respect to eigenvalue. You get Fi, right? So Fi is nothing other than derivative, your force, okay, or gradient. Minus of the gradient will give you the direction to go towards the minimum. So your H psi is nothing other than the gradient which guide you to go towards the minimum of psi. Okay, which means the derivative, so because you have to go down, no? Steepest descent.
Oh, so you are opposite of
Okay, okay,
gradient.
okay.
Yeah. You are not going that way, you are going this way. So steepest ascent would be plus, steepest descent will be this. So this is just to give you, simplest of the optimization algorithm. You can add fancy stuff to this. You can have Hessian to this. You can do approximate Hessians to this, Newton-Raphson, quasi-Newton-Raphson, conjugate gradient, okay, preconditioned conjugate gradient. So everything built on this simple equation that you can find out. Yeah. Okay. Machine learning. Okay. Right. Faster. Yeah. Simple. Yeah. So this is one way. So many code gives you an option to choose like conjugate gradient or steepest descent. Steepest descent, I don't know how many codes will have it today, but steepest descent is one of the most poor optimization technique, but only for teaching purposes I have used it, because there you can clearly see I'm getting the direction to go towards the minimum doing H into psi. Those issues are there. Yeah. When you teach first, you will not tell about the troubles. You will only tell about positive thing. So, right. So F phi I is made use, so which is something that I have already computed. I can do direct minimization, implement any simple algorithms to find the solution. Okay, but it is not that efficient unless you have a very robust optimization technique. That's what Professor Chetraj was saying, because it's very likely that you can get stuck in some minima and your optimization algorithm is not robust enough to take it out from that noise and get to the actual minimum. Okay. All right. But any point in this going down the hill to find the minima, make sure that at every point your wave functions are orthonormal to each other, because there is no condition to check it, because you're simply calculating H psi and taking that to go to the next step. But to the next step, I get some numbers, but be careful that new numbers that I got, new wave function I got is actually orthonormal. Okay, so that condition has to be implemented in your minimization algorithm. Is this okay? Yeah, sure. Yeah. Yes. Over all of. Exactly.
Then you multiply by delta of each, and then
Exactly. Yeah, it's that delta is a parameter. You can keep it fixed, but it'll be just a LAPAC routine. We'll simply take one matrix, and simply do that. I mean, it's just in one shot, everything will be done on a.
so if you are having
Yeah.
plane waves,
Right.
You will be taking derivative with respect to n plane waves
Correct.
or n star.
In plane waves.
N
Yeah.
plane.
Yeah.
And then changing each
I mean,
coefficient and going.
actually, this is in G space already, as I told you. So you can say directly use that actually to go down.
Yeah. So
Yeah.
whichever space,
Yeah.
you vary
All of them, all the degrees of freedom. Absolutely.
Here it looks
Very
very simple.
simple. Yeah. Of course, it's one dimension, but honestly speaking, in a code also, it is just a one-line Laplace routine. It's as simple as this. Okay.
Yeah, it should be kept in mind. So
Yeah.
radiate in that
Yes,
n-dimensional
n-dimensional space. That entire space. Okay, I think most of you are quantum espresso, Abinit, VASP people. I don't think they are using this. I know some module is there on quantum espresso which does the minimization. Is there? Yeah. So, but most of you will be doing what is called a subspace diagonalization. So they cannot take this entire G space to do it, but do a small subspace and diagonalize that and improve that eigenvalues one by one iteratively. And one of the most robust techniques that people use is Davidson diagonalization. Okay, so I don't have time to go through it, but if m is your number of eigenvectors that you are looking for, then it scales only n m square. So you can choose that residual that space in which you would like the dimension in which you would like to create this subspace, and you keep improving one by iteratively until you get the actual solution. Okay, so there are ways in which you can check whether I have reached convergence or not. Okay, I'm again not discussing those details. Those are practical things, but those are done and dusted years and years ago. So you can simply check it out, and it's very simple actually. Okay, in this algorithm, what I wanted to stress is there is a very important trick that Davidson has used, and that thanks to the G space formalism, because here there is, so to say, preconditioner. So preconditioner means it's like you're conditioning, you're kind of telling, okay, which direction to improve, because you've made only a subspace. You're taking only, instead of 1 million times 1 million matrix, you're simply taking 500 times 500 matrix and doing the eigenvalues. And how will that, solve this whole problem, right? So you have to keep improving that solutions that you get. So to get that direction, you need actually the eigenvalues of that Hamiltonian matrix. And the nice thing about our plane waves is the kinetic energy is so high that you can simply approximate that matrix by a diagonal matrix. Okay, the preconditioning that Davidson used is using that approximation that it is kinetic energy is dominant in all the Hamiltonian that you have. So you only pick the diagonal elements and make the preconditioning. And this is the success of Davidson, without which practically it would not have happened actually. So that is why I have gone to G space. I told you that why I went, again back to the G space, although I did everything in R space. But why did I go? Because now I can do these approximations and solve these iteratively diagonalize. I get the eigenvectors and eigenvalues. Okay, so there are other, Davidson is one of the approaches. There are other approaches also, but I think many codes are using Davidson only today. Yeah. So you don't have to select. So the code will automatically select. So it should be large enough, but it should not be small enough. So I don't know what algorithms they use to pick the size of that subspace. I practically don't know. How exactly that's the algorithm used there, but the whole fundamental idea is solely to pick a subspace to do that. I think you may also have options to increase the subspace, but yeah. Huh. Right. Right. No, Davidson, that's different actually. That's not. So because that's the direct. When it uses similar preconditioning to go down, but this works completely differently. Yeah. Okay, so I don't know exactly how they choose. Yeah. It is possible. Yeah, I think it is called Krylov's subspace or something. Yeah, so there will be a keyword related to that. I really don't know how these codes are implemented this, but there is some. Mhm. Conjugate gradient and Davidson come together. Direct minimization. Yeah. So it's all up to the programmer to. So there is also another way of using molecular dynamics to get to the minima. There's another way of okay. I think that's also there. Carparnello dynamics. You can also. Yes, that's also a possibility actually. Because with the finite temperature given to the variables, you will anyway go down very quickly in the direction of the gradient. That's another way of doing it. In all these steps, when you are not doing the direct diagonalization, you have to just be careful with the orthonormality constraint. That's all. Okay. So now coming to the earlier question, how are you going to deal with the core? What is the problem with the core? The core, this is a textbook example of the core of some atom. You can see that the core atoms are quite localized. The wave function is quite localized. Okay. The valence one is quite delocalized and has nodal behavior near the core. Okay. So there, one thing is it's all localized, nice and beautiful. So why do you have to include in your calculation if somehow you can take care of the core charge in your computation through some alternative manner actually? Yeah. R space. R space, yeah. Correct.
But when you go to the G space,
Ah.
you can see which one was like restricted to very small domain that would get spread out.
Correct.
Which one was spread out in momentum space that would get
Correct.
So what you would think that whether it is localized in small domain.
Yeah.
You have to
In the R space, yeah, correct. That's why I will come to that. Where how do you deal with the pseudo potential? Actually, yeah. So now, if we can somehow, because they are not going to involve in your chemical bonding directly, right? And they'll take a score only, even if this hydrogen atom is interacting with a zinc or something, right? I mean, or not hydrogen atom, some other atom. So core electrons will still stay there. Hydrogen atom, oneness orbital will interact. Nothing else is there. Okay. So, so the core electrons, we can just leave it, and somehow the density due to this core electron can be accounted to the nuclear charge. Okay. Then we don't have to include these in our calculations, so the number of electrons would decrease. But that's less of a problem for me. The more complicated part is this oscillating behavior of, or the node that is there on the higher angular momentum of the valence electrons, which is what you are going to treat explicitly. What is the problem? The problem is that since the function is changing rapidly, you need high frequency components in your expansion of plane waves, or more G vectors will be needed to be there in expanding, because there's an oscillation, right? If it is just something like this, the number of Fourier components that are there to represent such a function will be much less than what is needed here. I think it's also a small exercise that you can take sine of x and sine 10 of x and see how many Fourier components will be there. The answer is already there in the question, but but you can figure it out, right? I mean, so you need more high frequency term, which means high G vectors, high value G vectors will be needed to expand such a function. If the potential is also varying like this only, right? I mean, if the wave function is changing like this, the density will be changing like that, and the potential will also be having these kinds of behaviors. So this means more cutoff, and we would like to not go there actually. Okay, so two things. So single bullet, can we aim these two birds actually. One is don't include the core electrons because I don't care, okay, only consider the valence one, and somehow I don't want these things to be there actually, oscillations to be, nodal picture to be there. Nuclear, I'll come to that actually. It is included in pseudopotential in a different manner actually. Okay, so one simplest way to look at it is a frozen core. Okay, frozen core is just the core electrons are completely frozen. Okay, so less electrons, less orbitals in Kohn-Sham orbitals, straight, simple. Okay, how do you implement this? Very simple. Now that electrons sitting in the core is already part of the charge of the core, because that core electrons have gone to the nucleus, inside the nucleus. So the nuclear charge has increased. You just have to account for that charge, right? As simple as that. So simply add the charge density distribution into your Hartree potential, right? That's where you have seen rho of R into rho of R. So if you add rho of R there with the charge of the core, that's why he was asking, have you included the core, right? Because there I did not introduce pseudo potential, but now I know I am removing the core, I am including the charge density into the rho, okay, so that it is there in the Hartree potential. Nowhere else I have to do anything, right? Very simple. But issue is that it will require large plane wave cutoff again, because the valence guys are having node. When there is a node, the problem is that you have to bend, right? The wave function has to bend to reach to that node, so means more kinetic energy, right? So you have to have large, your G cut will go crazy. Okay, now I have to go a little fast because otherwise we will not reach to the end of the talk. So if I have a way to create a smoother wave function instead of the actual atomic wave function, so now I am talking about atoms sitting in, I mean I have, let's say, a lattice of copper. So I'm simply asking about the copper atom orbital, one of the orbitals, some angular momentum. Okay, you can see there is an oscillation, and there are nodes here, there is another node here, and then it just goes smoothly. So I define a distance r cut. Okay, I'm going to say, let me figure out a way to till the r cut. I will completely replace this oscillating fellow with something smooth from somewhere. Okay, go to the market, I get this guy. Okay, the only problem is, only thing I have to be careful, the above r cut, it should behave exactly identical to the actual solution. Otherwise, my chemistry will go wrong, right? Because that's those valence part is going to decide everything else. So now you look at the potential. This is Z by R. Now it will be something else. Be smooth and like this. So for every atom, atomic orbitals, I don't know if you remember, you have a radial part and then you have got an angular part. We don't have to care about the angular part. YLM theta phi, everybody knows, YLM theta phi. So forget about that. We have to only look at radial part, atoms, atomic solutions, right? So I can, if I have to make sure that there is a continuity here, okay, I will implement a condition that this is called the logarithmic condition, logarithmic derivative condition, that the derivative of this log of this function at this r cut of the all electron wave function and the pseudo wave function is identical, so that I get, I get basically the same behavior at this point and beyond. Okay, what is this? This is 1 by phi, derivative of this is 1 by phi times d phi by dr. That's what I have written here. Okay. Derivative of phi with respect to r divided by the phi, right? So I'm just using this as my tool to figure out, is there a continuity of this two wave function? One I bought from the market, the other is actually the exact solution, which is R of R times YLM theta phi. YLM theta phi I don't care, I only look at R of R because that is just adding angular nodes to your solution, right? So I'm only bothered about R of R. So I got a new R of R, which I call it as pseudo R of R, which has this part, and look at how smooth it is. So now I can use this together with the frozen core. Then my wave function cutoff is going to be definitely lower than what is there before, because my function is now less oscillating. Okay. So it looks like, is it really possible to create such a function? Actually, it is possible, fortunately, that you can create a function, you can find a solution to this one. I mean, it's a one-dimensional Schrodinger equation, right? Because it's a Schrodinger equation of an atom on R space only. It's just R of R. You understand what I'm talking about? Just the radial equation, just the radial part only. Okay. So it is possible to have an R of R that follows these conditions. So rest of the details you look into the literature on what is the guarantee that you get something and so on. I had a few slides which I removed just to, so now there is one small thing also I wanted to make sure. It's not just the continuity. Whatever is my new function that I am employing, I get from the market, has to follow certain conditions also to make it generalizable for not only for copper but also for copper oxide, but also for copper chloride, or I mean, I don't know, maybe some some other material, okay, of copper. The copper pseudo potential I am creating now should also work for copper in all chemical environment. Okay, for which what has been figured, people have figured out that one important condition is what is called a norm conservation, and the norm conservation is simply the norm of the market pseudo potential to the actual solution. Okay, you just have to make sure that these are fulfilled. And how do you check it? You just have to integrate up to the, it's a very simple integral, right? It's a function as a function. It's R of R. It's very simple. I mean, you can just write a piece of code to do this, right? Simply square them, and up to the R cut, the norm, the density till that point is exactly identical to that of the. Okay. I mean, norm in the sense it's not that way. It's a norm of just to make sure that that density of this core part is identical.
Up to infinity also it will be the same one.
After that, the function is sure. Yeah, but that is a little loose condition. I mean, in the sense, this is a specific condition, right? I mean,
right, but
so.
if you say both are normalized,
Huh.
outside they are the same.
Huh.
So they reduce to this.
I mean, the norm is the same. Yeah, norm is the same. Yeah, correct. Yeah, but the functions are different inside. Yeah, correct. Exactly. Correct. Exactly. Correct. That's true. That's anyway true. I mean, that's what I'm saying.
I mean, R cut is not necessary.
No, bar cut is needed actually. So that's what I wanted to stress, because your function is different below R cut. The only thing that is common between the two is the norm. Yeah. So that's but the norm entire range is same. Yeah, that's true. Yeah. No. No, then no. That yeah. So I'm coming there actually. So you need to be transferable. Your copper is true for any copper. Okay, and that is now I am sure you've seen people could achieve it because you don't care from where you got the pseudo potential. Somebody built pseudo potential for you. You are simply using for copper oxide, copper chloride, perovskites with copper, everything, without even thinking, oh, is this really true that the gold? I know, no. That will not work. And next, so that is what we call transferable. Two things ensure this. If you are creating a pseudo potential by yourself, these are the two things, but nowadays nobody creates it. So one is the norm conservation and also the derivative, the logarithmic derivative as a measure to really make sure that they are all fine at the point of R cut. The other is the softness we just mentioned. It should not have any nodes. It should not be varying rapidly. It should be as smooth as possible. Okay, so that you can use less number of plane waves. So you must be knowing the ultra soft. So it's ultra soft actually. Okay. So I'm coming to ultra soft actually. So now coming to Professor Chattera's question, what about R cut? What do you choose R cut? This is very tricky actually. I mean, I have myself created pseudo potentials, so I know I can get different types of pseudo potentials with different R cut. So you have to be very careful that if you are generating, your R cut is chosen such that it is indeed transferable and your plane wave cutoff is small. So these are two different things, right? If R cut is small, it is transferable because it's almost behaving like atomic solution. But R cut is small, you have to pay at the number of plane wave. Your computations will get expensive and expensive. So you have to play around with these two things. You will never be able to satisfy your soul by saying, oh, I'm getting exactly identical results. You will always have to compromise on certain things. Okay, check molecules, take different molecules, take band structure, look at the band cap. There are few checks you have to do before you accept, hey, this is a great pseudo potential. But today we don't do it, where we all cross our fingers saying that whoever did that pseudo potential have done a great job. I'm sorry?
Compared to normal pseudo potential.
I'll come. You're going too fast. Okay. So I mean, this we will not go in detail. I mean, okay. In practically today, we generally use norm conserving or PAWs. Both I will briefly tell you. So here you have this pseudo potential. The way the pseudo potential is created, it has what is called a local part. Local part is not is just an R dependent potential. Okay. It's only R dependent, but this is actually also you need a non-local. Why non-local? Non-local means it is angular momentum dependent, because if it is a car, you have to pay some fees. If it is a lorry, you have to pay another fees. So the way you can treat different angular momentum with different, with in a different manner. So you can see that here this operator picks the individual angular momentum, and you include the pseudo potential due to that L. So it's an L resolved pseudo potential actually. Okay. By the way, I forgot to tell you how do you get this pseudo potential. I already told you how to get the pseudo wave function. How do you get the pseudo potential? I missed reading one line. It is very simple, because you have H psi equals E psi. You invert the Schrodinger equation, you get the potential. Right? Your potential times psi you already have. So you can invert to get the V. Okay. So that is how all the code does, except one pseudo potential that I know, which is the Gyodeker pseudo potential. If you are a CP2K fan, I think most of the CP2K calculations are done with Gyodeker pseudo potential, which is representing the pseudo potential as the sum of Gaussian. Okay, so there the inversion is not possible. So it is not done by inversion, but just by an usual fitting actually. So that's a different thing. But otherwise, you have the pseudo potentials are just done for each angular momentum. You can invert the Schrodinger equation. You know the psi, okay, and you know the E. What is the E? E is your all electron energy. H psi equal to E psi. E is your all electron energy. Psi is your pseudo wave function, but potential you don't know, but you can get it. H has this. H already has the potential. You can simply invert that Schrodinger equation to get the potential. Okay, so I missed that part. So that is how you are getting this. So when you are creating pseudo potential, you are already creating this. Okay. Now this is just a theory. In practice, it's very expensive to implement this. I think there are also earlier versions of pseudo potential where this is implemented in the code, but today nobody does it. So people use simpler versions of this. One is Kleiman-Bylander form. What does it do? It is not going to do that kind of, so I mean, I call this as fully, non-local, okay? Because there is no angular term here at all. I mean, so I have changed this part with some projected functions, beta, and some predetermined coefficients. So it's very easy to implement. So your pseudo potential contains these projectors. Projector means what? It's some function like a Gaussian function. Okay, you take a wave function, you take a dot product of that. So, okay, it's waiting for to get a dot product. You give a function, takes a dot product of beta to that function, give you that. Okay, you multiply that with this number. Okay, whatever you got, you are multiplying with this. I mean, you have psi, no? Psi v psi, so that psi will come, multiply this, and you got the pseudo potential energy. So that's how this should be read. So this is already determined for when you are creating the pseudo potential. The beta functions are created, and these weights dj's are predetermined. So the way you include this non-local part is, so to say, pre-programmed. You don't have to do any complicated business. So the D's are fixed, the betas are fixed. So your pseudo potential file contains these quantities. This is very easy to implement, very quick also to calculate the pseudo potential. Just by fitting. Yeah. Yeah. Correct. Yeah. Yeah. Yes. Yeah. It has to. But it is not, you can have any number of channels. It's not just restricted. Any number of channels of, I mean, we call it channels. So you can have different beta functions. So for one angular momentum, let's say L is equal to 1, you can have more than one beta functions. It's not strictly sum over L. Okay. Earlier you had to go through each individual angular momentum, whether it's an S or a P or a D. Okay, you treat differently. Here, I mean, it's for P, you may have not just one projection, maybe you may have multiple projectors actually. So this sum is not strictly over SP, whatever is your valence. Yeah. Wow, that's very difficult to say. I think it's kind of a non-linear fitting, right? I mean, you try to get as much as close to your atomic wave function, as much as close to the eigenvalue, right? So it varies actually. Okay, now actually I will go a little quick. I'm sorry, ultra close atoms. Oh, this R cut will be much smaller than any of those bonding distances. So that you can be sure. I think if you choose it very large, then you may have to think about these problems. Okay. Hmm. Really, on a collision? Maybe that kind of, I don't know. I mean, I cannot think of a collision of that sort where your inner orbitals will also get into the bonding. So as a chemist view, I don't see that's going to happen. You can have relativistic effects where you will have to think about the core, but I don't know. Is it possible to? Huh? Right. I don't know. Maybe you have a problem. You can talk to me. I don't know of any problems where it's needed actually. So maybe I'm wrong. Okay. So now people were unhappy. So some of the pseudopotentials of the category I mentioned are Trolley-Martin's pseudopotentials. I think many of you would have used Trolley-Martin's pseudopotential. So it goes there. Gothic pseudopotential I'm not discussing because it's different category. But then the cutoff, the plane wave cutoff was quite high. People were unhappy. So then came what is called ultra soft pseudopotentials. The ultra soft pseudopotential is very interesting. It says that forget about norm conserving. But if you forget about norm conserving, we already know things can change. Because you see the charge due to this part up to R cut is different to that of this. Then how can you represent a core of an atom without maintaining the norm of it, right? I mean, it's not possible. If I say 2 electrons are in the core, I need 2 electrons to be in the core, also provided by my pseudopotential. So the trick which Vanderbilt did, which is amazing, which also led to many other inventions later, is to introduce corrections to this. Okay. These are very painful corrections if you program this on a computer, because what you do, you take the Cornsham orbitals, you apply an operator very similar to the beta functions that you show and each of these beta functions depend on whether it's S or a P type and so on. It makes the computation expensive. Okay, so basically the take home message is you can do a correction, post correction, okay, because the solution that you get, psi that you get at the end of the solving Cornsham equation is useless, I mean, so to say, right? Because if you take that psi and do integral dr psi star psi, you will not get density because your core density is already spoiled. So you have to correct that wave function by some post fix, okay, and so that part is going to come in every place wherever the density is going, right? Wherever in our Cornsham, Hamiltonian we build, everywhere these corrections have to be included. So it's going to be computationally a bit expensive than the norm conserving pseudopotential. But the success was the cutoff was so low, it was so low that it still give you a significant computational benefit even for very strong. I mean, oxygen is one of the difficult element to take in terms of pseudopotential. Yeah. 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 Density. Yeah. So, yeah. Psi square. Yeah. Yeah. Correct. No. That will not work. No. Your pseudo potential itself is wrong, no? That is the problem. You have taken that to create the pseudo potential, which itself is wrong. So it's just not the norm, but the potential that you are going to include as. Yeah. Ha.
What is the value of the integral of the exact one?
Correct.
You simply take that value. Let's say this is k.
Correct.
Multiply this with just k to the power minus. The pi you multiply with k to the power minus.
But you have to. No. But you will not get the V correctly. That's the problem. Yeah. So. Okay. So this idea of post correction using appropriate operators, to this has led to what is called a PAW approach, the famous paper of Blocher. And I think all the WASP users would be now only, and maybe even quantum espresso people. The idea is very simple. You have these Cornsham orbitals, which is not all atom. Okay. So what you do is you ask to correct atom wise, include correction is sum over all the projectors, by the way, but you think of each atom has some contribution, or atomic orbitals. I mean, these are atomic orbitals. Phi i's are atomic orbitals. Many orbitals, yeah, right. So you take the actual all electron atomic orbital and you subtract that with the approximate pseudo wave function orbital, which gives you the correction that you need to add to the missing all electron part. Add them to get this. Okay, so this will help you to have very smooth function using the same idea that I mentioned, and on the top of it provide a way to correct your solutions to the quality of all atom. Okay, so it is really like you ask what is the petrol price change here. Okay, I go to UP, I assume the same price change will be applying there also, but it may not be true. Okay, but it's a good guess, right? Implementation is horrible. Implementation is very complicated. Yes, but it works beautiful actually, and people have spent years to make the codes efficient, and WASP is a example for that, where it works really nice. But otherwise, it's in terms of a programmer, yes, it's going to be very painful. Actually, all these projectors that you have to have, I mean, implementing them is not easy actually. Just one last bit. There is also something called a latest version of norm conserving Vanderbilt. Vanderbilt, I said, forget about norm conserving, but then Vanderbilt came up with a new idea of creating a norm conserving pseudo potential, but with a very low cutoff. The idea is just in a simple terms, you look for high frequency components and explicitly remove those high frequency components by going to Fourier space, and that's it. It works beautiful. I don't know how many of you have tried this ONCVs. Implementation is very simple because it follows exactly the same as the norm conserving pseudo potential. The code that uses norm conserving will work for ONCVs, ONCV, and cutoff is as small as the ultra soft pseudo potential because it has smoothened. But great thing is norm conservation is fulfilled. Okay, so you can see the cutoff now that Torre Martins, the traditional norm conserving, something like 80 Rydberg for water molecule. Okay, strictly speaking, maybe a little more, 120 should be there. Okay, but poor man's sense. I mean, okay, it's publication quality, but not if you are very picky fellow, maybe you have to go to 120 because oxygen is not always soft. ONCV in that sense, it's 40 Rydberg. Maybe. No, there is nothing. It is just that the beta D of the norm conservation is needed, yes. But that's simple to implement. Yeah, because here you have to correct every line of the code for projecting back because your wave function itself is not correct in the ultrasoft. So overlap, you have to recalculate. Yes, so all of those becomes issue actually. So basically, I mean, you will see something like if it is something like this.
And this also transfer.
Yeah, transfer. Yeah, ultrasoft, right? Yeah, absolutely. Yeah, ONCVs, I personally tested on one of the DFT codes we developed, where we found it's very, very good actually. I mean, I don't know how many of you have tried yourself. You can try it out, but it's pretty cool actually. I mean, very simple and of course PAW cannot be beaten. If there is a code like WASP, I don't think you should think about ONCV. I mean, that's my suggestion. But I'm not an expert where I have played a lot with PAW, so don't take my advice as a try it out by yourself. But PAW is very, very efficient. Okay, now This should have been the first slide, but I intentionally kept to the last slide because at least this should be the take-home message. That why plane wave? Because there's no doubt it's good for periodic system because the plane wave themselves are periodic. It follows as the, it's perfectly, right? There is no basis set superposition error, which is a scary thing for Gaussian basis, okay, or anything atom-centered basis. You have to have these corrections to be done. When you do molecular dynamics, there is no overlap. So there is no derivative of overlap with respect to nuclear coordinates coming. So there is no Poulet force also. So you've got a very clean forces. The Hellman-Feynman forces, right, are seamless. I mean, it's perfect for plane waves. Basis set superposition error. What happens is that in the space, if you have atom-centered basis set representation, you have basis set sitting on the top of atoms. So there are spaces where the basis set is incomplete or not perfect as other places, because your Gaussians, let's say Gaussian basis, the Gaussian sitting, let's say two atoms are sitting next to each other. So at these regions, you have very good basis set. But things far away, you don't have. Yes, behavior is different. So many plane wave people, especially with physics background, they don't like Gaussian basis set for exactly this reason, because you don't know what is the basis set. I mean, you can say Gaussian basis set, but what is the quality of the basis set is unclear. So what people do, what people who uses Gaussian basis, they use diffuse functions. They use yes, and try to make sure that the space of interest is uniformly covered. Most dangerous one is when an atom is moving in this region. Then the forces are different in one point and another point, which can create disastrous results. So especially when you do molecular dynamics, this becomes a serious factor actually. It's a uniform. Yeah, so there's no problem. And I hope I convince all the equations are simple to implement. You can implement, I mean, just with the Python code. And parallelization is also easy because mostly what we do is only Fourier transform. Multiplying two functions in R space or G space, you use Laplace routines. Fast Fourier transform, you have already libraries available. So there's nothing much to do to write a plane wave code actually. So problem is when you deal with isolated system where the system is not replicated, there you have to somehow take care of that you get an isolated density, and this density is not interacting with the neighboring. You can do some tricks on that Hartree potential that I showed. You can do some tricks to make sure that they are not seeing the mirror images actually. Okay. You need pseudo potentials. With PAWs, that problem is actually solved. So otherwise, you have to really worry about pseudo potentials. And then, okay, if there is a large vacuum space, you still have to fill those vacuum space with your plane waves. You cannot say that, hey, don't fill anything here, right? Because you don't have any control on the R space. Your real space is already booked, right? You have already defined your lattice vectors. So in the G space, they are already naturally there. So there's no way you can say, I'm not interested in this part of the real space. Don't put any basis set there. That's not possible. I didn't tell you about the exchange correlation function because I think it is going to come later. So where you will see that it's also very easy to implement. And there are some practical issues in implementing exchange correlation functions, but those issues are already solved, so numerical issues and so on, but it's already taken care. Yeah, so there are many codes actually. I mean, so and pseudo potentials. You have also, I mean, you can see that almost all the entire periodic table is covered. So and you can go and pick the type you need, the format you need. I think nowadays people are happy with the UPF format, the unified pseudo potential format, which you can download from Quantum Espresso site. But be careful because of my own experience generating pseudo potential. Really be careful with pseudo potentials. Okay, you do a test before you blindly use them and get some results, because things can go really wrong. Okay, just don't worry about this. Just I have put all the equations. You look how simple they are. I mean, this is non-local part. This is local part. These are small integrals. Okay, small integrals on the projectors that I talked about. Very simple to implement this. Right. So, okay. How many minutes I have? Half an hour. Okay. Okay. So, as I told you that the forces on nucleus is very clean with plane waves because basis sets are not centered on atoms. Okay, and you know about Born-Oppenheimer surface. You can think of like atoms are static. Okay, and if you solve the Schrodinger equation, you get the energy of that state, right? So if you have energy, you can also calculate force because you just have to calculate del E by del R, the force, right? So every atom, so E Constant divided by del Ri, this is my nuclear coordinates. So I can calculate this gradient for every atom that I have. So not just the energy, but also the forces. And these forces are anyway used for optimizing structure and things like the nudge elastic band, optimization of structures. All you compute this, and it's not so complicated. It's sorry, force, yeah, force is this. The gradient is this. So now this is assuming Born-Oppenheimer approximation, which means the energy when the nucleus is moving, the energy of that system can be simply computed by solving psi h psi. This is a movie made by Suraj in his first year of PhD. So I thought I will show. Thanks, I am still using this very nicely, showing for H2 plus how the Born-Oppenheimer surface is discovered by this, right? I mean, two atoms are coming close to each other. You can see the psi square also. Okay, you will think for H2 plus what happened? Why this density is also on the other nucleus, which Suraj can answer if you ask him later. Okay, anyway, so you can nicely see this. So why don't I use this fundamental idea that the energy, the total energy, is a function of nuclear coordinates, and I can calculate the gradient to evolve the nucleus classically. Okay, so I move classically like an apple falling from a tree. I can predict when the apple will be after t plus delta t. Force is equal to mass into acceleration, right? So I can integrate that second order differential equation. I can predict where the apple will be after some time or the nucleus will be after some time for each of the nucleus. I need force for it. Do I have the force? I have the force. It's negative of the derivative of Constant energy with respect to R. Very simple to evaluate. It's because you already know the functional form of energy. You just have to take the derivative with respect to R. You will get another equation. It's already added. Yeah, that's why actually somebody you only asked actually. Am I preparing for? You are asking. Yeah. In this case, yeah, correct. Actually, for periodic calculation, it is important to add at that stage where I showed. Yeah, because your nuclear density is sitting here and it's replicated. Right? So that sum over that electrostatic interaction over lattice you need to calculate. You have already calculated. Okay. So the only problem which I was telling Suraj also, that the only problem is that this density is also seeing the same density for, because Q1, Q2 by R, right? So this density is interacting with the same density that I have corrected actually. That is there was a self term there which corrects that interaction. Okay. So that's why I did not explain to the students, because if they look at the eval summation, how the eval summation is done, it's exactly identical. So I leave it to you just for reading how eval summation is, and then you can see that there is nothing. Okay, so I can calculate this potential from any method. I mean, Hartree-Fock or DFT or anything. So, but we are talking about plane wave DFT, so we will calculate from plane wave DFT. So this is my second order differential equation. Mass into acceleration is the negative of the gradient. This is del by del R. Okay, and I have the force So I just have to integrate these equations of motion. If I integrate the equations of motion, I can predict where the atoms will be after the real time in the clock, I mean in my watch, the real physical time. Okay, 1 picoseconds of my watch, I can say, okay, after 1 picosecond, where will be in that nucleus, I can exactly predict. But classically, it's not quantum dynamics actually. Okay, so I'm not solving time dependent Schrodinger equation for the nucleus. That's why I said I'm using Born-Oppenheimer approximation. Okay, within that, I can simply use a classical evolution of the nucleus, and it works well. With hydrogens, we have to be careful, but in most of the cases, let's say even a reaction that happens inside a catalytic system, I can predict it with reasonable accuracy without going for a quantum dynamics, but staying with the classical dynamics. So now you know everything about E. Just believe me, taking a derivative of that expression with respect to R is also a trivial exercise. It's just one page of derivation, but you can do it actually. Okay. So so what is actually, it's a marriage of Schrodinger and Newton, right? So every time step you solve Schrodinger equation, Cornsham equation. Okay. So you get the forces, then you ask Newton to move to the next time point, exactly the way Apple was following. Go to the next step, solve the Schrodinger equation. For in our case, I mean the Cornsham equations. Sorry. Oh, that is true actually. Yeah. Only under Born-Oppenheimer. Yeah, correct. So now you will ask, I will get when you classically evolve a classical equation of motion, it's a second order differential equation. So you predict dr by dt and r as a function of time. So you get velocity of atoms also predicted for free, okay, and you are also getting positions predicted for obvious reason. I mean that's what you are interested in actually. But with velocity, you can calculate a very interesting thermodynamic property, which is the temperature of the system. So now we are getting a new quantity in our business, which is the temperature. This is actually the temperature that people measure with the thermometer, T, okay, which is related to the average of kinetic energy. You are averaging per degree of freedom, that is half kBT. Equipartition principle. Beautiful actually, right? I mean, but this, what we just learned, you use classical equations of motion, you not only predict where the position is, but what is the temperature of your system actually. If it is zeolite or I don't know, water or something that you are doing DFT calculations, every time step you do DFT calculation, but you get velocities. Use that velocity to predict what is actually the temperature of the system. So you can do one more thing, which I am not telling. You can also say, hey, look, my temperature is 300 Kelvin. You make sure that at every time point the temperature is 300 Kelvin, or on average it's 300 Kelvin. Then the classical evolution can be tweaked that way. So which means you are predicting what will be the R and Ri dot, but you can predict with the constraint that the temperature is 300 Kelvin, which means you are predicting the structure and dynamics of system at a temperature of your interest. Quantity, that is the most important. Right. Still, but so that is why, yeah. So I had a nice slide on that, but I am not. It is not used there. So you have to use statistical mechanics is exactly meant for that, right? I call it as a barbel fish. I don't know if you know this famous book of Hitchhiker's Guide to Galaxy. There's this human beings is getting kidnapped by an alien. They get into the alien vehicle and they can't understand what the alien is talking about, right? So experimentalist is talking about temperature, pressure, and you're doing microscopic simulations where you will have things written in double precision numbers, you don't know how to talk to the chemist. So I call statistical mechanics as a barbel fish. In this story, they are given a fish which they put it in the ear. So the nerves will communicate with the fish, and fish will communicate with the sound waves, and it gets translated naturally. Okay. So yeah, 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 yeah. Yes. That also, yeah, that is also needed. Very important actually, that you just generate random numbers which are from a Boltzmann distribution. So you have, let's say, 100 atoms. For each 100 atom, 3 degrees of freedom. Every degree of freedom get one number from the Boltzmann distribution randomly. Doesn't matter. Absolutely. You know, everybody has to. Yeah. Yeah. No. For every degree of freedom should follow the Boltzmann distribution. That's the canonical ensemble actually. So on canonical ensemble, it has to fulfill. I mean, yeah. Yeah, bonded or not. Yeah, no. That's not true actually. No. It's not like that. Every degree of freedom should follow canonical distribution. Yeah, that's true. I mean, otherwise the ensemble what we are talking about is garbage actually. Yeah. Yes. You have to maintain actually. Yeah. So a very simple way you can think about is the Langevin equation. So where you are having a velocity friction is applied to the system as you are going on average. The Langevin equation will follow a distribution, and that would make sure that the average temperature is T. So it's very simple ways. Just add random numbers to the system from that distribution, so that it on average it follows that distribution. That's the classic thermostating. Yeah, absolutely. From Korn-Shamick. Exactly. Correct. Exactly. Right. Also changing. Exactly. Okay, so yeah, every step you have the frictional term. These Langevin terms are there actually. I mean, both. It can be both plus or negative, because your distribution has both sides. So one way to integrate the equation of motion is textbook example. X is equal to x0 plus t times velocity plus half at square. You remember half at square? Same thing, okay? X t plus delta t is x of t plus v of t times delta t plus half at square. Okay. In this, what will you get from Korn-Shamick equation? This is the position predicted. This is the current position. I already know the current position. Okay. This is velocity, which is another degree of freedom like position, which also you have to supply. Like Professor Harbola asking, how did you start with? You have to give some initial velocity. You give that initial velocity. That is independent to position. Okay. So you have position and velocity, and position is predicted, velocity is predicted. So this is where our DFT comes, right? Because it's acceleration. Acceleration is force, right? You already saw that equation. So you get the force. From force, you calculate the acceleration, plug into this equation. It will simply keep running and provide you the positions and velocity predicted as a function of time. Same thing, you need a predictor for velocity also. This is also in classroom physics you have learned actually. So
the first one you are taking acceleration at t, second one at
t plus t, yeah, exactly. So you put an initial coordinate of your system. So if it is water molecules, let's say you use your chemical intuition, physical intuition, or just use random numbers to create initial structures, Cartesian coordinates, right, for every atom. Then of course you can calculate the force, because you have to solve the self-consistent field calculation, DFT calculation, get the energy and force. And with, of course, when you have force, acceleration is free. then you have to set this initial velocity. So position is one thing, velocity is another thing. So this is taken from Boltzmann distribution usually, and then you simply predict the new velocity. Dt is the parameter. Acceleration is already coming from Consham DFT. Verley also is possible, yeah. So we do that in 2 steps. I skipped that part actually. So for practical purposes, you can, it's somewhere here. Yeah, so this is, I was just saying this is identical to do it in 3 steps because of simplicity in terms of equation. Numerical part only. You can just load R to R in memory. You don't have to create a new memory in your system. So that's all. So you keep doing this, and every time when you update the position, be careful when position is updated, energy is changing. Born-Oppenheimer approximation, right? So you have to solve Consham equation. So you have an SCF.
R change by taking velocity in the middle and then
Yes,
velocity.
correct. Exactly. That's it. So one step of MD requires one SCF. Okay. So just a simple derivative, so simple test. This is the Hamiltonian, classical Hamiltonian, kinetic energy plus potential energy. You take time derivative. Okay, this is dE by dt. Total energy is kinetic energy plus potential energy. Yeah, kinetic energy plus potential. Potential energy is our Consham energy. Right. You can show that d by dt has to be 0, which means total energy has to be not varying as a function of time. Okay, this is very important. Whatever the atoms are doing, your total energy is flat. You see the kinetic energy is changing, potential energy is changing, but perfect conservation of energy. Otherwise, you will not be simulating anything useful. This is where I'm coming. It's not that easy. Okay, so for any approximations you do to calculate energy, be careful. If you are taking that into molecular dynamics, your total energy is conserved. This is just to show you, if I do Born-Oppenheimer MD, which means every step I am doing SCF calculation with different convergence criteria. Okay, if I actually do a very poor convergence, see the conserved quantity, kinetic energy plus potential energy is going somewhere else, which means that this configurations I got may not make any sense. Okay, so this is a very important thing that you converge. It's not like geometry optimization. In geometry optimization, you can leave with a higher cutoff and say that, oh, it's nearly converged, fine. But for molecular dynamics, the forces have to be really 0, and this is very difficult with many basis sets, and you cannot also make any mistakes like the Poulet force ignored in the force. If so, you will actually see the total energy go crazy. So any code that you use for Born-Oppenheimer molecular dynamics, any parameter, any cutoff that you choose, please check if the energy is conserved as a function of time. So what scale will you keep here? I mean, you can keep the scale, because see, it depends on how you look at this, right? So if I look at a smaller y-axis, right, then I will be seeing oscillations, right? So I see. Sorry. Okay, I don't know actually. Yeah. Okay. I don't know. Maybe I'll learn from you after that. So yeah. So this is very critical actually. So to test this. Yeah. So just wanted to this total energy. So you have to check. So usually the cutoff that you choose, wave function cutoff that you choose to say that SCF is done. I'm talking about the SCF convergence criteria. So for a geometry optimization that you choose may not be ideal for Born-Oppenheimer molecular dynamics. So that you may have to go at least one order less. So you have to check this actually, that the energy is indeed. So the easiest way to check is you plot two things together. So you plot the potential energy. So this is the potential energy, which is identical to the Cornsham energy as a function of time. Okay, and on the top of this, you plot the total energy, and that total energy, if it is not a straight line, or if it goes like this, not good. This is okay. Why I am plotting potential energy? Because you get this axis range is also an important factor to say if it is a flat line or not. So you have to just look at in terms of the energy fluctuation unit of your system. Yeah, so that's all. Okay, it's just very simple. So here, gamma point calculation. Okay, I assume large enough unit cell. Okay, randomly structured water molecule. Okay, I can just choose. First of all, I have to create this system. Okay, and usually when you create such a liquid system, solid is trivial because you know the structure of solid to start with. You only have to optimize a little bit about the lattice vector and so on, right? But for liquid, the problem is that how do you start, right? So you need to have, you don't have a static structure of a liquid. It's a dynamic structure, right? So how do you start? So you ask what is the density of this for the temperature that you are simulating, and you pack these molecules based on the interatomic distances and so on, pack within this cubic lattice with a number density that you are expecting from experimental data. From experiment, you know, with this pressure and this temperature, this is the density. From that, you calculate the number density. Then per liter or per angstrom cube, how many particles will be there, you know. So you pack for your 10 cube, 10 into 10 into 10 angstrom cube, how many water molecules? For example, for water, 32 water molecules in 10 into 10 into 10 box gives you 1 gram per liter. Okay. So then you choose any quantum mechanical method. Be careful. Plane wave, we are talking about plane wave. So use plane wave, then no worries, your forces are correct. If you are using CP2K, I'm not blaming CP2K. Be careful because your basis sets are hybrid basis set, but you are largely doing everything in Gaussian basis set, right? So in that case, be careful your basis set is sufficiently large enough to not to have any total energy drift. Correct. So there are a couple of checks we have to do. One is that for water, we know there is first solvation shell, second solvation shell, and third solvation shell. So you have the neutron diffraction data from experiment. You can easily run a simulation and check whether you are getting a radial distribution function that is nearly same. So for liquid is therefore tough to simulate actually. Yeah. Exactly. Yeah.
What is your superset?
This one. Yeah. But I mean, if I actually, I had a movie. I think I don't know if I have that. Okay, just I will come to this. I will show you an example where it's a bit tricky actually. So we are almost finishing. Yeah, I mean, then you choose appropriate parameter delta t. So delta t is usually 1 femtosecond or half a femtosecond because that time step is sufficient to simulate the changes in the force because you are integrating equations of motion, and if your forces are rapidly changing as a function of time, okay, then you need to have smaller time step. So the thumb rule is if you have one oscillation, okay, you just make sure that there are some 20 to 30 integration points in time step. Okay, there are 20 to 30 time step is there for one period of oscillation. So this is the thumb rule actually. Okay, so you can choose delta t accordingly. That works. So if you have hydrogen atom, the OH bond is vibrating like crazy, 4,000, 3,800 centimeter inverse, so very rapid motion. So you will have to go to half a femtosecond time step in many cases. Okay, but hydrogen or deuterium, why should it matter? Chemistry is not dependent on hydrogen or deuterium. So change it to deuterium, right? Then use 1 femtosecond mass. Chemistry, you're looking at chemistry only, right? That's why you're reading ab initio MD. So it doesn't matter actually. IR spectrum, there is a problem. If you're looking at any dynamic property, then you're screwed actually. You can't do it. Then you have to stay with half a femtosecond. So any system with hydrogen atoms, usually half a femtosecond is the safest. Okay, again check the energy conservation. If the time step is large enough, you will not get an energy conservation like this. Okay. Okay, so then there are other things like thermostats, which I was just explaining to you. There are different types of thermostat which make sure that as you are integrating the equations of motion, the average temperature is maintained, average pressure is maintained, and things like that. So biostat, thermostat can be added to the equations that I just showed. But that's just an add-on to the physics that we just discussed. Initial structure in X-ray structure for solids, no problem. If you are looking at an ion diffusing through the lattice of a solid, very trivial problem. Okay, take the lattice, throw in the ion which is diffusing anywhere, but for liquid problem, look at what information you have in terms of experiments, in terms of density, what is the G of R, the radial distribution function, which you get from neutron scattering experiments. You look at the neutron scattering experiment and look for how the first solvation shell, second solvation shell, how far it is, right? What is the length of the first solvation shell, second solvation? So your box should be large enough, and number density should be maintained to reasonable values. For gases, just randomly use random numbers, place the atoms randomly anywhere, like helium, for example, if you would like to simulate. Okay, initial velocities, as I mentioned, from Boltzmann distribution. This is just randomly picking numbers from a distribution. Boltzmann distribution, you know, right? So it's just the velocity is distributed from minus infinity to plus infinity as a Gaussian curve. So if you have two atoms, you pick 6 points. Why 6 points? There are 6 degrees of freedom for two atoms. Pick randomly 6 points and you use it as an initial guess. Okay, this is just a complicated example. This is where I throwed one electron into water. Okay, and it's kind of interesting problem also, highly reducing environment, right? So what happens to the electron? So this is a periodic box of 64 water. I am using hybrid density functional theory. I think you will learn about hybrid density functional theory later. So I've used that to predict what will be the position of each and every degree of freedom at every instance of time. So you can see the time here. And this RG is a property that I'm measuring from the trajectory that I'm getting. Trajectory means R, the positions, as a function of time. Okay, I'm using that to simply predict how distributed is the spin density. So one electron means open shell calculation, hybrid calculation. Okay, 64 water, quite a large system. You're doing DFT every step. Okay, and to calculate and look at the spin density. Okay, so right now you see it's all over the place. Blue color is all over the place. As we launch the simulation, look at what happens. You can see the time counter. It's nicely localized. Okay, there's electron. Should be the electron here because that's a spin density. And beautifully, you can see this number matches with experimental data perfectly, because experiments have been done from 1970s on this system. And the structure of how water has reoriented to accommodate this negative charge is also very interesting. Okay, so you can simulate these kinds of very interesting problems, which experimentally, very difficult to understand what is the thing that I'm getting, and very complicated in today's time. Yeah. Added electron, yeah. Okay, so that naturally goes into the background charge due to that eval summation. Yes. Yeah, because in this such a small system, you can't add any. Yeah. So this is just to give you, a few examples from my own paper. I'm not advertising it, but just to give you some examples of it. I was lazy. I could have worked hard to find good papers of other people, but so this is just to tell you that I can simulate a high pressure, high temperature environment in my system and look at things in details which otherwise simply not possible. This is a high pressure water at high temperature exposed to iron sulfur, this pyrite, and I could see how various chemical reaction happens on that. Again, thanks to plane wave DFT to do this. Okay, that I could do this actually. This is again for catalysis. You have again quite complicated. It's just gas phase here, but you can use molecular dynamics to see how two atoms are reacting. Throw this into your system, run forever, and see what happens. Okay, so you can predict new pathways which otherwise would not have been possible. This is another interesting thing. If you have titanium dioxide, you remove one oxygen, so you have a polaron. You have again an electron. Okay, and then kind of how that electron is diffusing. So experimentally, people have seen that this is moving between layers of titanium dioxide. So which we could also see, how that look at how the charge is changing as a function of time. So you can see all these kinds of very interesting things through this ab initio molecular dynamics. Yeah. Okay, so last slide. So you can, I can recommend few good papers, but I'm not saying that it's comprehensive. It has everything, but I mean, especially if you are not a first year PhD student, but a second year, third year, fourth year, this book is good. Okay, but if you're a first year PhD student, that book is scary actually. So don't go there. You can use that book for getting references, but to read that and appreciate it, you have to go to maybe second year, third year, where you have some hands-on experience. But the book is a Bible actually for people who are working on plane wave DFT. Its implementation, how the code works, and how molecular dynamics can be used to study complicated processes. Okay. And then I don't know, I think you all possibly know this paper. It's a fantastic paper actually, big volume paper again on plane wave DFT. Okay, I'm not discussing about DFT itself. Then Richard Martin's book is very good to start with actually. Some parts are not very well explained, but then for implementation aspects, you can also look at this DJ Singh's book, which I don't know whether it's anymore published, but should be available in libraries actually. I find these are quite good in understanding how plane wave DFT is actually implemented and used today. Okay, I think with this I can. That's all actually. Yeah, that's all. Yeah, thank you. Thank you so much. Thank you. Questions?
Since you mentioned polaron,
Yeah.
so I have a question in that sense. So, as sir asks that when you are adding explicitly an extra electron in a system, you are compensating that with a background charge.
Yeah.
Now that is great if you are going in a LUMO, like where it is delocalized over the whole system.
Correct.
But when there is a polaron formation, the negative charge is getting localized in the supercell, but the positive charge is delocalized. So there is a possibility of dipole, like fictitious interactions.
Correct,
So
correct.
how will you take care of that?
I mean, right now I don't have an answer how to take care of that. I don't see any ways you can handle it. except that you actually use much larger supercell and see if the things are converged. If you, we
But
have
sir,
done very.
I mean, larger supercell will aid the fact that your two negative charges will not interact.
No, I mean not replicating the same thing, but one charge. For example, if there is an electron in solution, you increase the charge so that overall effect will be less, right? So, but not to add another electron to it. So this is one thing we have checked. I will tell you one interesting example we did was iron 2 plus in solution, again unpaired electron charged. We kept increasing the box, energy never converges. So the only way you can solve this problem is to extrapolate to the L goes to 1 by L goes to 0 limit actually. So that is the trick that we used, but I don't know if there is any clean way of handling. Okay. Okay. Yeah. I heard some implementation is there in WASP also in this, yeah. Yeah. But I have not followed it up actually, so I'm sorry.
Any other question, clarification? No, he is going to be with us today also. Please.
I just have a general question with respect to the splitting of the bulk water. So when you treat the bulk water, so when you have more number of waters, do you use do you use grid points to place it, or do you use the Van der Waals directions accounting and then place it randomly? Because with respect to the area and density, you can determine the number of water molecules.
Right.
But placing it in appropriate,
correct.
how do you deal with that?
Correct. So nowadays there are ways to get this by a software called PackMol. Okay, so PackMol, yeah. So it uses the intelligence of how one molecule is interacting with the other one, and then aligning that. But it not always gives you the perfect structure. Right. For all other purposes, you do exactly this way, that you place it in a regular grid and then
kind of. If you use grid, the rotation is restricted.
No. That's only to create the initial structure. After that, you are free now. Yeah. Of course. Absolutely. Yeah. But that's a trick. Like I don't know if you have seen that helium atom simulation, 2D helium atom I was showing you. So there also, I have just placed the helium atom on a regular grid. That's the easiest way to handle it. Initial structure, yeah. After that, you equilibrate. We call it equilibration until every property that you are interested is converging as a function of time also. Too many convergence check. You are already worried about K point, plane waves, and pseudo potentials. There are too many things to check. Yes. Yeah, at the starting. Yes. Yeah, you're right. Yeah, actually now I think we are living in a very exciting time of ab initio MD people because we have now got lots of tools. So one trajectory is more than enough. Only point is that you have to look for, there are many techniques available today. So you just have to identify what is the ideal technique to sample configurations efficiently for the problem that you have in hand. So one simulation should be more than enough, but it's always advisable to check convergence of estimates, free energy barrier and so on. Because in ab initio MD, doing multiple simulation is yeah, correct. See, usually what sir is asking is you are doing ab initio MD, it's computationally expensive, so the time you cover generally is only picoseconds, but reactions happen in seconds, hours, and so on. So how do you bridge this gap? So there are set of techniques called enhanced sampling techniques, which accelerates the conformational sampling, which means from t to t plus delta t, you are exploring configurational space, you are sampling the configurations are more efficiently than what a Boltzmann would do. Okay, so you kind of tweak Boltzmann to kind of go aggressive in terms of picking up configurations. From that, you have to reconstruct the Boltzmann statistics. Like, so you get a distribution which will not look like Boltzmann, but then you have what is called reweighting techniques. Will map it back to Boltzmann distribution. Then you can predict things like free energy at temperature T and things like that. So referees today ask you to run multiple simulations to say, oh, this is the number. But in India, to do ab initio MD simulation itself is difficult, and then to repeat it is punishment actually. So, but today looks like that's the standard. Yeah.
Thank you, Nisanth.